Okay, so we're diving deep today into the world of semiconductor engineering physics.
Yeah, exciting stuff. Right at the heart of pretty much all modern tech.
Exactly. And this is a listener request. They sent over this huge stack of material.
A lot to unpack for sure.
So our mission, I guess you could say, is to pull out the most important and
Yeah, the most fascinating, the coolest insights from this stuff about semiconductors.
right, because I mean, these materials, they really do power our world.
They really do.
So first off, what are we even talking about when we say semiconductor?
Okay, well, it's funny because semiconductors, they're kind of like the Goldilocks of materials.
Goldilocks. Okay, I like that analogy.
Right, they're not too conductive like, your typical metals,
Okay.
but they're not too insulating like glass or something like that. They're right in between.
So somewhere in the middle.
And the really cool thing is we can actually control that conductivity.
Ah, so you can kind of tweak it.
You can tweak it, you can tune it. That's what makes them so powerful.
Interesting, because I was noticing in the materials, there wasn't like one single definition.
Right.
It seems like, depending on who you talk to, like a materials scientist,
Yeah.
they might focus on, these crystals with certain imperfections.
Mm-hmm.
Then you've got physicists who are looking at this thing called the electronic band structure,
Yes.
talking about valence bands and conduction bands and energy gaps.
Okay.
And then electrical engineers, they're focused on how electrons in these holes actually move.
It's a great point you bring up because it's this multifaceted nature of semiconductors that makes them so interesting and also allows us to really, understand and then use them.
And that leads right into the applications because, I mean, these things are everywhere.
They are absolutely everywhere.
You've got your everyday appliances, your rice cooker, your gaming consoles,
Mm-hmm.
but then also, life-saving medical devices, renewable energy transportation defense systems.
All built on semiconductors.
And it all boils down to these tiny little transistors and integrated circuits.
Yeah, you find them in your computer, in your smartphone.
Yeah.
It's the core of it all.
And the materials themselves, I was surprised by just how many different types there are.
Oh, yeah.
You've got your basic silicon germanium, but then,
Yeah, your elemental ones.
then you go into these compounds. Gallium arsenide,
Gallium arsenide, indium phosphide,
gallium nitride, silicon carbide.
silicon carbide.
It just goes on and on.
The list keeps growing, and they all have their own unique kind of strengths and weaknesses.
And one thing that really struck me is just how sensitive they are to their environment.
Oh, yeah, very much so.
I mean, we're talking about their conductivity changing with temperature, light, magnetic fields,
Mm-hmm.
even tiny amounts of impurities.
Absolutely. So that's
Yeah.
why, controlling all those factors is so important when you're
Yeah.
manufacturing these things.
Absolutely. So let's dig into some of those fundamental properties. And I guess the first one that
Yeah.
really stood out to me was crystal structure.
Yes, absolutely. The way the atoms are arranged, that
Yeah.
ordered arrangement,
Right. So this crystal lattice thing.
the crystal lattice, yes, it's like the architecture of the material.
Okay.
And it really dictates how the electrons can flow within that material.
So different semiconductors, they have different lattices, I guess.
You have different patterns.
Okay.
Like you mentioned, silicon has this diamond cubic structure.
Right, where every silicon atom is connected to four others.
Exactly, 4 bonds.
Yeah.
Very strong bonds. And that specific arrangement, it has a certain scale to it.
So this lattice constant.
The lattice constant, yes, and that influences all sorts of properties of the material.
Okay.
But here's the thing. These perfect structures,
Mm-hmm.
they're never quite perfect in reality.
Right. There's always going to be some flaws.
You're always going to have some imperfections, dislocations, impurities, grain boundaries.
And these actually mess with the electrical properties.
They can mess with the electrical properties, the optical properties as well.
Ah, so that's why we're always trying to make these super pure, perfect crystals.
Exactly. Especially for things like integrated circuits where you need things to
Right.
behave very predictably.
Behave in a very controlled way. Absolutely.
And this crystal structure, it seems like it really dictates the electronic band structure.
It directly shapes it. Yeah.
So in a solid, I guess, the energy levels of all these individual atoms, they kind of blur together.
They broaden into bands, yeah.
Into these bands, and then you've got this gap between them, this forbidden zone.
Right, this energy gap, which is so crucial.
So that's the band gap.
That's the band gap. And the size of that gap, it actually determines whether a material is
Oh, okay.
a semiconductor or an insulator.
So where does a semiconductor fall on that spectrum?
So semiconductors, they have a relatively small band gap.
Okay.
Small enough that, at room temperature, some of those electrons, they have enough energy to jump across that gap. And that's what allows for some conductivity.
Okay, now we were reading about direct and indirect band gaps.
Yes.
And it seems like the direct band gap, like in gallium arsenide, it's more straightforward when it comes to light emission. It is. Yeah, like in your LEDs and lasers.
Right.
So in a direct band gap material, when an electron falls back down across that gap, it can release a photon, directly release light.
Oh, so that's how LEDs work.
That's the basic principle.
Right.
But in an indirect band gap material, like silicon,
okay,
the electron needs a little help. It needs to interact with a lattice vibration.
Oh, wow. So it's a more complicated process.
A bit more complicated, and it makes light emission less efficient.
So that's why silicon isn't used for LEDs.
Right. It's not ideal for LEDs, but it has other amazing properties that make it so valuable for other applications.
Now, this band gap, it seems like it also plays a key role in the electrical properties.
Yeah, for sure.
We were talking about conductivity and resistivity.
Yes.
So in a pure semiconductor like silicon or germanium,
yeah, your intrinsic semiconductors,
you need enough thermal energy to get those electrons up into the conduction band. But that's not very efficient at room temperature, is it?
No, it's not very efficient at all, and that's where doping comes in.
Okay, doping. So this is where we're adding impurities.
Intentionally adding impurities, yes, but in a very controlled way.
So we're not just making it dirty, we're adding specific things.
We're adding very specific impurities to enhance the conductivity.
Okay, so how does that work?
So let's say you add a group V element, like phosphorus or arsenic. Those atoms, they have an extra valence electron compared to silicon.
Okay.
And that extra electron, it's easily excited. It can jump up to the conducting band. And that creates what we call an N-type semiconductor.
N for negative, because of the extra electron.
Exactly, where electrons are the majority charge carriers.
Gotcha. And then if you add a group 3 element?
Like boron or aluminum.
Those are missing an electron.
They are missing an electron, so they create these holes in the valence band.
Which act like positive charges.
Which act like positive charges, yeah. And that gives you a P-type semiconductor.
Okay, so you've got your N-type and your P-type depending on what you dope it with.
Exactly. And the amazing thing is, even tiny amounts of these dopants can dramatically change the conductivity.
It's amazing how these tiny impurities can have such a huge impact.
It really is. It's all about manipulating those energy levels and the availability of charge carriers.
Now let's talk about light, because semiconductors, they seem to interact really strongly with light.
They do, especially with photons that have enough energy to overcome that band gap.
Okay, so if the photon's energy is greater than the band gap,
then you can have absorption.
Okay.
Where the photon basically knocks an electron up into the conduction band, creating an electron-hole pair. And that's the principle behind solar cells and photodetectors.
So that's how they convert light into electricity.
Exactly. And then you have the reverse process.
Okay.
Where an electron in the conduction band falls back down to the valence band. And it releases energy. And that energy can be released as a photon, as light.
So that's how LEDs and lasers work?
Exactly. And again, the direct band gap materials are much more efficient for this.
Right, because it's a more direct process.
Exactly. No pun intended.
And the color of the light, it's determined by the band gap energy.
It is the larger band gap means higher energy photons, which means shorter wavelength light.
So blue light has a higher energy than red light.
Exactly.
Okay, and then there's this thing called the refractive index.
Yes, the refractive index.
Which describes how much light bends when it enters a material.
Right, and that's really important for optical devices.
Okay, and then beyond all this, you've got thermal properties, like how well they conduct heat. And mechanical properties, like how hard they are, how elastic they are.
Absolutely.
Yeah.
All these properties are important for how these materials perform in devices.
And how we can actually manufacture them.
Exactly.
So it seems like it all boils down to the behavior of these tiny little electrons.
Yes, it's all about quantum mechanics.
Right, the quantum world.
So in a crystal lattice, those electrons, they behave like waves.
Okay.
And they can only have specific allowed energies which form those energy bands we talked about.
And then the gaps between them.
And the gaps between them and there, all sorts of cool concepts, like the Brillouin zone.
Right, and effective mass.
Which describes how the electrons respond to forces within that lattice.
So it's not just their actual mass, it's how they act.
It's how they behave within that crystal structure.
Okay, and then when you get down to really, really small scales, like nanometers.
Yeah, the nanoscale.
Things get even weirder.
Things get even weirder. You get these quantum effects.
Right, things like quantum confinement and tunneling.
Exactly, and these are actually being exploited to create new types of devices.
Wow. So let's talk about some of those devices, because we've covered all this amazing physics.
Yeah, let's see how it all comes together.
So starting with diodes.
Okay, diode.
They use this PN junction, right?
They do. You create a junction between a P-type and an N-type semiconductor. And that allows current to flow in only one direction.
So it's like a one-way valve for electricity?
Exactly. And that's used in all sorts of things, like rectification signal processing, LEDs.
LEDs. So that's how LEDs work.
That's part of how LEDs work.
Yeah.
Yeah, you need that PN junction.
Okay. And then you've got solar cells.
Solar cells, which harness the photovoltaic effect,
right,
where light creates those electron hole pairs. And then the PN junction separates them, creating a voltage and a current.
So it's like a built-in electric field.
It is. And the efficiency of a solar cell, it really depends on the band gap of the material.
So you want to match the band gap to the energy of sunlight.
Exactly. You want to absorb as much of the solar spectrum as possible.
Okay, and then LEDs and lasers, we talked about those a little bit. They rely on that light emission from the PN junction.
They do.
And the color of the light depends on the band gap.
It does.
So choosing the right material is key.
Absolutely. You need a material with the right band gap to get the color you want.
Okay, and then sensors.
Sensors exploit the fact that semiconductor properties are very sensitive to external stimuli, so things like light, temperature, pressure, magnetic fields.
Okay.
So you've got photodetectors where light increases the conductivity.
Yes. Thermistors, where the resistance changes with temperature.
Okay.
Strain gauges, where the resistance changes with stress.
So you can measure how much something is stretching or bending?
Exactly. And Hall effect sensors, which produce a voltage when exposed to a magnetic field.
Wow, so it's like a whole toolbox of sensing possibilities.
It really is.
Yeah.
And the choice of material really dictates what kind of sensor you can make.
Right, so silicon, it's kind of the workhorse for microelectronics.
Yeah, it's the dominant material for transistors and integrated circuits.
Right, because it's abundant and we've gotten really good at processing it.
Exactly. We've got decades of experience with silicon.
But it's not ideal for light emission because of that indirect band gap.
Right.
So for high-speed applications and lasers.
You might turn to gallium arsenide, which has a direct band gap and much higher electron mobility.
So things can move faster.
Things can move faster, yeah.
Okay, and then germanium, it's good for infrared detectors.
It has a smaller band gap, which makes it sensitive to longer wavelengths. And for high-power, high-temperature electronics?
You might use silicon carbide or gallium nitride.
Okay.
Those materials have wide band gaps, high breakdown voltages, good thermal conductivity.
So they can handle a lot of power.
They can handle a lot of power.
Okay, and then indium phosphide, it's used for high-speed communication.
Yes, because its band gap is ideal for fiber optic wavelengths.
Wow. So many different materials, each with its own unique strengths.
It's amazing, isn't it?
So we've covered a lot of ground here, from crystal structure and band theory
to electrical and optical properties.
And it's all rooted in quantum mechanics.
It all comes back to those fundamental principles.
And these properties, they're the key to designing all these incredible devices.
The transistors, the diodes, the solar cells, the LEDs, the sensors.
It's amazing to think that all this technology is built on manipulating these tiny little electrons.
And we're still learning new things about these materials all the time.
Exactly. And who knows what kind of breakthroughs are just around the corner.
It's an exciting time to be in this field.
It really is. So what other fundamental properties of semiconductors might we learn to control?
In ways that we can't even imagine right now.
I guess that's the big question.
It is. And that's what keeps us all going.
Thanks for joining us on this deep dive.
My pleasure.
We'll see you next time.
See you then.